This is the design for a high-temperature metal-to-ceramic seal for the life support system intended for use on the International Space Station. An astronaut breathes about 0.84 kilograms of oxygen per day. The current life support system uses oxygen reclamation and CO2 removal with approximately 40 to 50% efficiency. This process produces a waste methane stream which is currently exhausted into space. Reusing waste methane would increase the current efficiency. Honeywell is developing a methane pyrolysis reactor to return waste methane back into the cycle. This would increase the recovery of oxygen to 100%. This reactor separates methane into hydrogen gas and solid carbon, which must be removed periodically. Pyrolysis occurs in a vacuum at very high temperatures where traditional metals cannot survive. Because metals are more reliable than ceramics under tension, a metal seal is used. Ceramics are difficult to seal with metals at high temperature due to a thermal expansion mismatch. Cooling methods must be kept to a minimum.
Our application system requirements. The inward air leak must not exceed 4.7 standard cubic centimeters per minute. The seal shall operate at a minimum of 500 degrees Celsius. The seal shall operate at 100 torr. The seal shall operate for 150 weeks. The seal shall survive 150 cycles from 500 degrees Celsius to room temperature for carbon removal. The seal shall take no more than 1 hour to be opened and resealed by an astronaut in microgravity. The seal and reactor tube shall not exceed the dimensions of a 68 by 41 by 33-inch box. The seal shall not place more than 150 megapascals of tension on the reactor tube. Our derived application system requirements. All gastric sealing surfaces shall have a surface roughness of 32 AARH. It shall not exceed a surface roughness of more than 68 AARH in accordance with Parker's specifications for proper sealing. The ceramic tube shall be designed to account for a size tolerance of plus or minus 1% to be molded. The system shall be serviceable with a 3/4 inch wrench.
3 initial designs were roughly sketched and evaluated against system requirements. A purely locking ring design was selected and drawn in SolidWorks. Materials selected include silicon nitride for the reactor tube and Inconel 718 for the exterior flange and lock plates to optimize material strength. Due to budget constraints, a scale prototype was designed to model the thermal expansion of the actual design with confidence. The final and prototype designs were modeled and simulated in SolidWorks as well as verified through ANSYS simulation. The prototype was created and tested for leak rate and thermal integrity at scaled temperature for the prototype material. 450 degrees testing temperature for the stainless steel prototype was chosen to simulate the similar thermal expansion for Inconel at 500 degrees C. The sealing interface design consists of 2 different materials. Silicon nitride ceramic was chosen for the reactor tube itself, while Inconel 718 was chosen for the rest of the metal components. For the prototype, 1018 cold rolled steel is used as a stand-in for the silicon tube, where 303 stainless steel is used for all of the metallic parts.
Design and simulation. We developed this design around the properties of Parker's E-type gasket. These are gaskets used in gas turbines and other high temperature applications, and they are designed to maintain a seal with fragile, even separating flanges. As you can see by the compression-decompression curve, they are highly elastic compared to other gaskets. They can spring back to maintain a seal if sealing surfaces move away, and they have very little plastic deformation, making them relaxation resistant. E-type gaskets also have extremely low clamping loads, and they can operate at temperatures well above 850 C, making them perfect for this application. The design idea was to utilize the properties of the E-type gasket and the properties of frictional interfaces to construct a lock ring geometry that does not overstress the ceramic tubing during loading, while also allowing for parts to expand freely, preventing stress concentrations due to restricted thermal expansion. We modeled the worst case sealing separation in ANSYS at 500 degrees Celsius, and we estimate that at 500 Celsius the separation is 0.006 of an inch, which is within the specifications for separation of the E-type gasket. We modeled the worst case loading for our design in ANSYS by applying the maximum force that the gasket can exert on the 2 sealing surfaces at 500 degrees Celsius. And what we found is that the maximum von Mises stress anywhere in the model is an order of magnitude below the activation stress for deformation due to creep. It is also well below the yield point for Inconel 718 at 500 Celsius. Likewise, solving for the maximum tensile stress for the worst case loading in our ANSYS model yielded a maximum tensile stress of 2 megapascals on the reactor tube, and this results in a 148 megapascal margin for the maximum tensile stress of silicon nitride. The metallic material properties development and standardization showed that at 500 Celsius, Inconel would creep 0.1% under 690 megapascals after 150 weeks. The finite element model shows that no portion of the Inconel will be anywhere near 690 megapascals, and we can conclude that the creep strain is negligible for our design. You can see by the figure at the bottom that the minimum stress on that figure is 20 ksi, which corresponds to about 140 megapascals. We are an order of magnitude below 140 megapascals, indicating that it's going to take much longer than 3 years for any creep strain to show up in the model in any significant way.
Start with a flange and slide the reactor tube into it. Insert the gasket into the groove in the reactor tube. Insert the seal plate into the flange. Twist the seal plate to align with the tabs. Thread 6 bolts in to evenly distribute the load and depress the seal plate. This will effectively preload the gasket so you can insert the lock plate. Insert the lock ring and twist to align with tabs. Remove the bolts and store. This completes the assembly.
Now on to the results. The overview. 2 tests have been done to observe the leak rates. Both contain a dry run and a temperature heated run. The dry run is to observe how the seal holds at room temperature. The temperature run is to see how the seal holds at steady state temperatures of 250, 350, and 450 degrees Celsius. Note that the E-type gasket was used in these tests. The allowable leak rate should be less than 0.42 inches of mercury per minute. Now on to the first test run. This time the gasket is going under test. The dry run had a leak rate of 0.75 inches of mercury per minute that lasted for a duration of 30 minutes. Now on to the second test run. This time the gasket is going under test for a second time. As you can see, the dry run failed at 4 minutes, so the seal did not hold its vacuum. Initially the value measured for the vacuum was 22 and it went down to 0. Next, for the temperature run, it was vacuumed multiple times as needed, and as you can see at the steady state value at 250 and 350 degrees Celsius, the leakage were over the leakage limit, so it fails. In contrast, at 450 degrees Celsius, the steady state temperature, it held under vacuum. Note that these temperature runs were at a span of 15 minutes instead of 30. Based on these 2 tests, it's very inconclusive if it's reusable or not, so therefore more tests is required.
In conclusion, the prototype successfully verified all system requirements at operating temperature. Although there were signs of possible gasket reusability, the data was inconclusive and more testing would need to be done in order to prove. The surface finish of the mating surface on each sealing part needs to be less than 37 arithmetic average roughness height. The flatness of the gasket mating surfaces must be within 1/1000th of an inch. Blanch grinding or stone polishing and lapping is required. The addition of a high temperature vacuum grease is a viable option to aid in sealing the system when any surface imperfections are present. Lower CTE materials may be a more suitable option as the stress loads have a safety factor of 100. The gasket used in testing had a Teflon coating, which was not recommended at the temperatures tested.